Hello everyone, in this video I will explain you how to simulate a closed loop control system with actuator limits in Simulink. So what you can see over here is the final result of my modeling, and I will teach you how to make this model. Here is my plant. It's a mass spring damper system, a classical example for illustrating control systems, and the part over here is my PID controller. Notice here that I have also included actuator limits. Actuator limits are a very important part of our model since they will enable us to simulate more or less realistic actuators, because every actuator cannot exert infinite amount of force or torque. Consequently, we need to limit the amplitudes of exerted forces and torques in our model. Before I start, I have to mention the following. It took me a significant amount of time to prepare this video. So if you like this video, or if you like the other videos I make, please consider to subscribe to my channel or hit the like button below. Okay, so let's start from the very beginning. Our first task is to model our plant, that is our mass spring damper system. The model of our mass spring damper system is given by the equation 3. M is the mass, Kd is the damping constant, Ks is the spring constant, and F is the force. So the transfer function corresponding to this model is obviously given by this equation, the equation number 4. Now, let us model this system in Simulink. So let's start a new model. We'll click here on a blank model, and let us close our model, the previous model, just to make everything to be clear. Okay, so the first step is to model the mass spring damper system. So over here, you can click on the library browser, and here you need to find the transfer function. So if you click here, for example, on continuous, you will see that you have here a transfer function. And you can simply drag your transfer function to your Simulink screen and you can drop it. Okay, so here is our transfer function. So this is one way for bringing up the transfer function block. Let us erase this and let me explain you a more convenient way for bringing up the transfer function model. You can just click somewhere on your screen and you can just start typing. If you start typing, you can start typing transfer function, and here you have several options. So this will be the first option that I will choose. So you can automatically, by just typing, select your transfer function model. Okay, so let us define our transfer function. We can see that our transfer function is basically a rational function where in the numerator we have 1 and in the numerator we have second order polynomial. So if we double click on a transfer function model, we need to specify the numerator coefficient. So since the first coefficient is in the numerator is 1, we'll just leave it as 1, and let us specify the denominator coefficients. They are M, let's see, Kd and Ks. M, Kd, and Ks. Okay. And let's click on apply and OK. Now, obviously, there is here an error. Basically, we can see that variable m as well as other parameters do not exist. We didn't define them. So how to define them? That's not a difficult task. So if you go back to our MATLAB screen, and if you open a new script, so I'll close this script or click new script, I can type my parameters. Okay, so I'm going to use the values that I previously defined. So they're 30, 5, and 10. 30, 5, and 10. Now, if I evaluate these expressions, these expressions will now be in my MATLAB workspace that you can see over here. And consequently, when you simulate the model, Simulink will know basically that these parameters are in my MATLAB workspace. So you don't need to worry about, for the time being, about this sign over here, warning sign, since everything is now in workspace. The next step is to add a feedback loop and to add our reference input. Okay, so to add the feedback loop, we will need an element here that will subtract two signals. So if you go back to original Simulink model, we need to introduce this subtraction module. Okay, so how to do that? Again, there are two ways. If you go in the library browser, you have math operations, right? And here, over here, you can basically see different options, and I'm going to select sum option. Okay, so here's my sum. Of course, another way for bringing the sum is, again, you click here in the window and you press sum. And here's our sum. This is how you can bring it up. Okay, so let's see what do we do. So if I double click on sign, I need to adjust my signs. So I have a plus and minus. Minus comes from the feedback loop. And then the next step is to connect my transfer function with my sum sign. So you can just simply do that by clicking here and dragging this button and pressing it here. Now let us expand our transfer function, since I want to show the form of my transfer function. And let's make this diagram to be a little bit nicer, since we'll need more elements here. Okay, so the next step is to add our input signal. So how to add our input signal, or the reference signal, or the set point signal? Again, I'm clicking here and I will type step. If I click on step, this will be my reference signal, and I will connect it with the addition sign. Okay, here it is. Now let us adjust the parameters of the step signal. The starting step time should be 0. The initial value is 0 and the final value is 1. And I will click on OK. Okay, now we have here the error signal, and we can start building our feedback control algorithm. So let us look into our control algorithm. So here's the general form of our control algorithm. This PID form is more preferable compared to the standard form because this form is more physically interpretable. I'm not going to explain in details what are these constants. Basically, they are kind of associated with certain physical properties of the system, such as reaction time, prediction time, etc. The most important thing here is to observe this part, k. If you multiply this, k times 1, this is our proportional gain. K, if you multiply the second term, you get k over sti, that's the integral term. And the term, if you multiply this, you get k std over 1 plus std over n. So this is the derivative term. Notice here that usually the derivative terms are given by std. However, this type of derivative action is not the most optimal one. Why? Because this type of derivative action will amplify high frequency signals. So instead doing a simple derivative, we have here a filtered version of derivative, right? So for low frequencies, this derivative actions acts as a pure derivative. However, for higher frequency control actions, this derivative action acts as basically a low pass filter. So we need to implement this block. Let's see how to do that. Okay, so the C of S is multiplying the error, right? It multiplies the error that comes from this part over here. So what do we need to do? We first need to model our integrator. So how to do that? Again, there are two ways. You click here in library, and here on continuous, under the continuous, you have an integrator. And let's bring this integrator. Okay, this is one way. another way to do that, you can click here and type integrator, and here's our integrator. Let's put it over here. Okay, now we see that the integrator term is actually multiplied by 1 over ti. So let us define these parameters, ti, td, and n, before we start bringing them to our Simulink model. So again, I go to my MATLAB script, and here I'm just going to copy and paste the values that I defined before. So my ti will be 20, td will be 0.1, n will be 10, and k will be 1000. Watch out here, I selected these parameters by tuning my PID control algorithm. You can initially select a large proportional gain and set some of these values to 0 or to large values in order to eliminate either derivative action or an integral action. However, for the time being, and in the interest of brevity of this video, I keep these parameters as they are. Okay, and let us evaluate this such that we avoid the warning messages. And let's look again into our integrator action. So let's first implement this term 1 over s times ti. So here, in our block diagram, we already have 1 over s, so we need to multiply this by 1 over ti. So we need to bring up the gain, right? So if you click here on the library, you click on math operations, you need to find the gain. So here's our simple gain, and we're going to bring it up here. Okay, I double click on the gain, and over here I will type 1 over ti. Okay, so here's 1 over ti, and you can see clearly that now Simulink recognizes that our parameters are in the MATLAB workspace, and Simulink is not creating any issues, so everything is fine. Okay, and here I will add this part. Okay, so we have this term, right? And we can connect this term to our error signal. Excellent. Okay, so let us now implement our basically derivative action. Here is our derivative action. To implement the derivative action, I go back to my Simulink model. I click here and I type transfer function. So here is my transfer function. I will double click and I need to implement the transfer function given over here. So the implementation is td 0 in the numerator, y0, because this term is written s times td plus 0 times some constant, and the other term is td over n and 1. The term in the denominator is td over 1, and actually it's not exactly td over 1, it's basically td over n and 1. Okay, here it is, and let's expand this part such that we can see this. Perfect. And let's connect this part to our error signal. Now it's connected to our error signal. Okay, so what's the next step? The next step is, of course, to implement a simple proportional gain and to basically add to these two signals. So let us first add these signals. Here under the basically math operation, we need to click on addition. So here's my addition over here, right? And to add this, since I only have 2 ports, I need to add an additional port. I can click here and I can adjust the list of signs since I have 3 terms to add, right? If you go back here, again, we have 1, 2, 3 terms to add, so everything is perfect. And I'll just connect these terms like this. Okay. And from here, I'll just connect it over here since it directly goes. Okay, now what do we have? We have 1 over STI, and we have this filter derivative actions. So to implement the final controller, we need to multiply everything by KD. Again, we will use the gain. I'll click here, click and select the gain. So here is our gain. And I need to enter the gain of K. So here I will just type K. And you should observe again that since we evaluated these lines of codes, the gains and other parameters are in MATLAB workspace, so Simulink knows and can recognize the parameters. Okay, here it is. Here is our gain. Okay. Now let's go back to original algorithm and verify that everything is fine. Okay, so we have this part, right? Now what needs to happen? We need to basically place actuator limits. This is a very important step that's often being ignored by people teaching control theory. Actuators cannot exert infinite amount of force, cannot exert infinite amount of torque, cannot exert current that's basically infinite in value. Consequently, in order to simulate realistic actuators, we need to put some constraints over here, right? And these are the so-called saturation constraints. Of course, there are other type of nonlinear constraints such as dead zones, some hysteresis, and other types of limits. However, we are not going to discuss them in this video. Just for illustration, we will place here the saturation limit. So if I click here, I can type saturation. So here is my saturation. Okay, now here if I double click, I will adjust my saturation parameters. They're going to be from 50 to minus 50. Okay, so here's my saturation. Now, in practice, basically if you try to analyze what's happening with saturations, saturation is a function that looks like this. So this is the input signal, and this is the output signal, Y. So if I place an input here that's smaller than actuation limits, my system will simply transfer that signal. However, if the control signal is too large, you will hit the saturation, and this will be limited. Next, let us connect the saturation to other parts of our diagram. So I'll simply draw an arrow by connecting these two parts, and here it is. My saturation is connected with other parts of the diagram. When you create your block diagram or Simulink model, it's always a good practice to name certain parts. So this basically block can be called saturation limits or actuator saturation. So if I click here, I will see here a small, basically text box, and I will type saturation or actuator saturation. Similarly, you can name this block as, for example, plant, or you can say mass spring damper system. Okay, and erase this artifacts. Oops, I pressed delete, and I shouldn't do that. Okay, so here's our mass spring damper system, and you can also name other blocks. In interest of the brevity of this video, I will not name other blocks. However, again, it's a very good practice to name all the blocks. Okay, so we are done. So let us simulate our system. We click on run, and the system is being simulated. However, we don't see any plots. So to bring the plots, we need to find the scope menu. So if you click here in the library browser, under commonly used blocks, there is a scope. So you can drag the scope over here. Another way for bringing the scope block is just to type scope. So let's see what happens over here, right? I'm going to basically connect the scope to my output signal. So this is the output of my plant, and I will connect the scope to that part over here. And let us run the signal or actually the simulation again, and let's see what happens. I will double click on the scope. Aha, here it is. Here's my system response. We can clearly see an oscillatory behavior of the system. And let us try a little bit to tune this response. So if you go back to our parameters, for example, to decrease the overshoot, we will increase basically the derivative action. So let's put here 0.3. Let us evaluate these sections. Let us go back to our model and let us press run. Okay, so here is our response that's basically being filtered right now by derivative actions. We can see that overshoot is decreased. However, we have here a steady state error. So to eliminate this steady state error, you will need to increase a little bit the integral gain of our system. And here you have to be careful since you also have actuator saturation, and you might need to have an anti-windup filter that I will not explain in this video, right? So let us run our simulation again. Let's see what happens. If you click here, we can observe that the steady state error is slightly decreased. Okay, now, beside tracking this signal, it's a good idea to track the actuator saturation and the signal that goes inside of the actuator saturation. So let's bring our scope here and let's connect our scope to the actuator saturation. And let us bring another scope and let us connect it to the input of the actuator saturation, input over here. And let's run it. So let's see what happens over here. We double click on scope and here's our limited signal. We can see the effect of saturation. Here the signal is being saturated and over here the signal is being saturated. Okay, let us see the signal coming into the actuator saturation. We can see that the signal value is extremely high at the beginning of our control. We can see huge values. So these values are sent by our controller. You can observe over here basically that the gain, the proportional gain is huge. It's in the order of 1,000. Okay. Next, I will explain you how to save these graphs. It's very useful to save these graphs. So the best way, if you click here on File, you can basically click on Print to Figure. And now you have a classical MATLAB figure. So we can adjust the line width by just basically clicking on our line, clicking on basically Open Property Inspector. And here under Property Inspector, we can adjust our line width and we can say, okay, the line will be equal to 2, right? Then you can save this file, save as a PNG file or as a FIG file, it's your own choice. And then you can import it in your report, in your paper, or in any other document. Okay, so here you can also adjust, for example, the signals that you're sending. So you can send, for example, signal equal to 5, right? So we want to move our mass to 5 meters, and let's see what happens. If you run the simulation, and if you look into our response, we can see that we are not able to move the mass precisely where we want, and we can see that the response of the system is much worse compared to the response of our original system, and this is due to the fact we have saturations in our system. So we can observe that most of the time our controller is in the saturation regime, meaning that to move mass further away from our equilibrium point, we need large amount of force, because we have a spring constant, right? We have a spring in the system. This means that the force has to take large values. However, force is always limited between 50 and minus 50. So this is the effect of nonlinearity in our system. Okay, that will be all for today. I hope that you like this video. If you like the videos I make, please consider subscribing or supporting my channel. Thank you very much and have a nice day.